So I'm going to talk about replica-mean field as you were just told. So that's going to be a little bit different than the previous talk because it's going to be about modeling. And basically, it's a point process-based modeling framework that I've been developing in close collaboration with François Bacheli. And we've been working on this for about 5 years now. And so I'm going to give you like kind of an overview of the method. And I know that on the program, there'll be talks that are going to be very closely related to that framework. So I hope it's going to be a good introduction. So, okay. So basically, this slide is just basically a word of caution when you do modeling in neuroscience, and it's that okay, it's a big task, and the system you're trying to model are gigantic. They have many different constituents, and all those constituents display tremendous heterogeneity. So so when you do modeling, you want to be humble, and you know that you're going to have to do a drastic simplifying assumption, and in doing so, you're going to throw away a lot of details, but okay, you have to do it anyway. So I'm just quickly introduce the kind of simplifying assumption I'm going to make, and then I will introduce the framework. So there will be a simplifying assumption at two levels, right? The first one will be at the level of the constituent, so the neurons. And I like to exemplify the ingredients I like to keep on a movie. And basically, if the movie was playing, okay. Well, the movie is not playing. So I'm going to describe what you were supposed to see. I mean, I don't know if you guys have seen that. This is like a Japanese fountain type of thing. And basically, it's supposed to receive water, go down, release the water, go up. And so basically, there's three ingredients to it. You want, if you think of it as a neuron, you want the neuron to continuously integrate its input, then interact with its surrounding in a punctuate fashion. So at some point, boom, you release everything. And then once you're done, you reset to a base state. So this basically memory erasure. And so you want those three ingredients, or at least I will ask that a decent neuronal model has those three features. And there's different flavor of that, right? You can have an integrated and fire neuron, you can have a rate-based neuron, and all different sort of neuron that have those three features will be rate-based in this talk, okay? So, so that's for the neuronal model. Now then, perhaps more importantly, you also need to make assumption about how those neuronal models are going to interact with one another. And that means you need to make assumption about the network. And here, we're going to focus on one of the most common assumptions that allow you to do a little bit of analysis about those models, and that is the mean field approximation. So the mean field approximation is a long story. It's been proposed by a computational neuroscientist, as well as mathematician and physicist and so forth. And basically, it consists in considering a simplified dynamics that will take place on the network of neurons that have infinite size. And for this dynamics to be well posed, you also need to make an assumption about the scaling of interaction. And there's typically two scaling hypotheses. There is the classical thermodynamic mean field hypothesis, which is that a neuron have an interaction strength with one another that scale inversely proportionally to the size of the network. And then there's another assumption that is valid for balanced models. And that assumption allows for like a less stringent scaling, which would be inverse of the square root of the system. So again, there's a lot of work on this, and it's very great work if you ask me. But there's also a few limitations to this mean field approximation, and those limitations are the reason why we try to develop or elaborate a different framework. I mean, not really different. We try to extend a little bit on the mean field approximation. So what are those limitations? So the first two limitations are the ones that are really problematic. The third one, a little bit less. So the first one basically is that by design, when you make a mean field model, you throw away the correlation. And correlation may be important in the activity that you're trying to simulate. So that's a problem. The second limitation has to do with the fact that considering an infinite size system is not neutral. And in particular, it's not neutral if you want to like study the typical behavior of a system. Because looking very far in time and looking at very large system involve taking two limits that don't commute with one another. And so that means that if you look at a very big system, you may end up looking at a system that is not displaying the relevant behavior that you were interested in, because ultimately, networks are finite, right? Even so, they're very large. And so the last limitation is that often you assume the mean field dynamics. You don't necessarily prove that like it can be reached within a good limiting process, and that can lead to considering dynamical equations that are actually not well posed. There's no physical system that will satisfy those equations. And so we look at those limitations, and that was the starting point of us developing a framework, was to say, okay, can we come with a set of models that will always be well posed and that may allow us to attack point 1 and 2? We're not saying we're going to solve it. We just hope that there was a chance that we can do something about 1 and 2. Okay, so in that model that we propose is the Replica-mean field model. Okay, and so I'm going to explain it now on a very simplified dynamic that belongs to a class of dynamic called Galvez-Lochabar. So basically, the concept of replica-mean field limit will not matter with respect to what model we're considering. I just consider this model because this is the simplest possible you can come about that display the kind of feature I required earlier in the introduction. Okay, so we call that model the counting neuron model. Okay, so here you have 3 neurons, and they interact with one another via interaction parameter mu. So each neuron has its own dynamics, and it's characterized by a single variable, which is a counting variable. And so what is that variable counting? It's counting the number of spikes it has received from other neurons since the last time it has spiked. So here's an example of the dynamics. Each time, like red guy is spiking, blue and green are coming up by 1 unit. And when either of those are spiking, you go down to 0, okay? And so then there's interaction between those neurons, because now each neuron emits a spike in linear relationship to their count. So the more spike you've received, the more likely you're going to be to spike. And that corresponds to assigning a stochastic intensity in this fashion with a linear form. Okay? So because of the correlation, it's very hard to actually entirely characterize this system. And it may be surprising, but it's already a difficult question. So then you would like maybe to do the next best thing, which is to find a dynamics that is closely related to that system, and that will be amenable to analytical characterization. And so that's the purpose of the replica-mean field approach. And that approximating dynamics is obtained as follows. So the idea is to say that, okay, I'm going to consider my system of interest, and I'm going to duplicate or replicate it. And here I'm just making a 4 replica model of my original system. So for the original system, whenever a neuron interacts, it will interact with the neuron it connects to. So that means that in principle, when a green guy over there would spike, it will send a spike to the guy within the same replica if I was modeling the exact dynamic. Now, the point of the replica model is that I'm not going to simulate the exact dynamic. I'm going to only simulate an approximating dynamic that I get by randomization of the interaction. So that means that when the green guy spikes, now it's still going to talk to a blue and a red guy, but it's going to pick those guys uniformly and independently across replica. And then I'm going to get the exact replica mean field limit by considering the limit of an infinite amount of replica. Okay? And so basically, this replica process is really the defining feature of the approach, right? And then there will be a different type of, numerical or computational approach depending on the model at stake. So why do you expect such model to simplify the dynamics and allow you to solve it analytically? It's because, as in any mean field approximation, you hope for asymptotic independence. Okay. So here I just show it numerically. I'm looking at the correlation between neurons in a finite replica model, and I'm just showing that the correlation vanishes very quickly with the number of replica. And this is due to the fact that by randomizing interaction, the likelihood of 2 neurons to talk to one another regularly is scaled like 1 over the number of replica. So they behave effectively almost independently. And actually, we have more than this. We have basically what we call the Poisson hypothesis, which is that in this sort of limit, if you are a neuron of a particular flavor in one replica, and you look at the spike you're receiving from a neuron of another flavor all across the replica, you will see that basically you experience those spike deliveries as if they were delivered from independent Poisson process. And independence here is with respect to the type of neuron you look across replica. And so that tells you that basically there's hope for analytical tractability because the arrival process of spike is well characterized. So now I need to say that at this stage, it's just a Poisson hypothesis because it's been conjectured in many models, and we've shown that it holds only for a subset of dynamics. And actually, there's going to be a talk later on this week about proving this Poisson hypothesis for discrete dynamics. But okay, it's intuitively true. It should hold, and it's also observed numerically. Okay, so we're gonna assume that. Now, if you assume the Poisson hypothesis, now you can use your replica framework to hope to solve analytically the approximating dynamics. So here I'm just going to show it, and I'm going to show what it involves usually. What do you have to do computationally to solve a model in the replica-mean field limit? And then we'll talk about point 1 and 2. So here is the full dynamic of the interacting system. So it has a joint stationary distribution, and it's complicated because of the interaction. It's hard to do anything about it. But we know a few things about it. So in particular, we know that we could look at the probability generating function associated to those counting variables. And because the underlying model is still fairly simple, it's linear, we know that it should follow some functional equation. And if you walk a little bit around the model, you can see that, okay, this functional equation that the generating function should satisfy is some PD, okay? And it's a linear PDE because we've chosen some linear stochastic intensity. And so in principle, if you want a full characterization of the model, you'll have to solve this. So it's impossible, and it's impossible because of the presence of non-local boundary terms here. And those boundary terms are the one mediating interaction. So what does replica-mean field does for you? Well, it maps this model onto one where the interaction are basically being erased because you have asymptotic independence. So you erase interaction, and so you map your model onto a collection of independent mean field model, where each mean field problem is of the following flavor. Like you're trying now to solve for a probability distribution of a collection of neurons who will output at some rate beta, knowing that they receive 4 times this output beta because everything is exchangeable. So, okay, so that's the simplest possible kind of mean field problem you can come with. And if you look in detail what form that problem takes, you'll see that basically you independent, it's like projecting this equation onto independent direction. And the resulting equation you get now is a simple ODE along each direction corresponding to each neuron. So now it's an ODE, there's nothing scary about that, you can solve it. The only potential difficulty about it is that now each ODE is parameterized by that red beta. That is perhaps the simplest possible characteristic of the dynamic we would like to characterize, okay? And so when you do a replica-mean field approach, the first step is to get to those equations, which there's a recipe to get them. You're not going to be able to always get them. That's going to depend about the model. And then once you have those equations, the goal is you have a scheme, a mean field scheme, and the goal is to solve for it. And you want to solve for it efficiently because you want to be able to do numerics. So I'm going to just show you what it looks like in this simple case where it's an ODE-based scheme. So okay, it's yes. Do you have any question? No. Okay.
No question.
So yes.
No question. Don't worry.
Oh, no question. Okay, sorry. So okay, it's always going to be the same. So what's going to happen is you're always going to have way too many solutions than you need at first. And so, for instance, in that case, you can look at the generic solution of this simple ODE, and you will see that, okay, there are tons of them, okay, you need an initial condition, and there's an infinite amount of possibility for them. But there's also this free parameter dependence on beta. So, but what those solutions have that is of interest for you is that they all have a pole in 0. And so that tells you that, okay, you have too many solutions because you have singular solution, and you should not care about singular solution because you're after a probability generating function which shall be analytic and will behave. So it's always going to be the same when you do a replica-mean field limit. You always have too many solutions, but you can throw almost all of them because you have to impose a requirement of analyticity. So in this case, there's only one form for solution that are no polling zero. So, and that's that form. And it still depends parametrically on beta, right? And you after the value of beta. So then all you have to do is to impose the normalization condition on that any generating function should satisfy. And then now you have a simple equation on beta, and that's it. You've defined the spiking rate that your neuron assume in its stationary dynamic. And from this knowledge of the spiking rate, you can actually guess all the moments of the dynamics. Okay, so that characterizes entirely the full dynamics. And so that's it. It's always going to be the same. What's going to change is that you're going to have more complicated equation to start with, and you're going to have to be a bit more creative to throw away the non-analytical solution. Okay, but one of the great benefit of this kind of approach is that you can apply that independent of the structure of the network. And so here I'm just showing an example about what you can do for those kind of model. So here I'm considering a feed-forward network. Okay. And I'm just comparing to exact simulation the rate that you obtain by using the replica mean field trick, and I compare it to also the classical mean field trick. And in that case, there are dense connection from one layer to another. So basically, there's both of them work very well, and there's no real benefit to go to a replica mean field rate, and that is because connection are dense, so that there's a lot of averaging going out, and it doesn't really matter that you keep track of the finite structure of the network. So it doesn't really matter that you know that you only have like, I don't know, 5 neurons that you receive input from on average. But now if you go to a feed-forward model where like now it's sparse and your activity is dominated by a few sets of large connection, well, then you see that's when like the replica mean field trick becomes interesting because now you outperform the classical mean field limit. And so this is just to like say that, okay, we don't claim that replica mean field is always good. It's only going to work for a subset of network, and it's only going to matter if you in a regime where actually finite size effect will be dominant. Okay, so that's it for the for basically the approach and like what is at stake when you're trying to solve it. So now let's see if you can do anything with this kind of approach to tackle point 1 and point 2. Point 1 being correlation in the network, and point 2 being like how to deal with metastable dynamics. Okay. So if you want to try to get a go at the correlation structure, you're going to be led to you're going to be led to something we call pair replica models. Do you have any question at this stage?
No, there is no question.
Am I going too quickly?
There is no question, I think.
All right. Is there anybody in the room?
Yeah. There is someone. You hear me or?
Yeah, no, I hear you, of course. No, okay. I'm joking.
Good. Don't worry, we are with you. You're not alone.
Okay, good. Okay, so yes. So back to the correlation problem. So replica mean field is a mean field approach, so it erases correlation. So it seems mysterious how you could like try to get at correlation within that framework. However, there might be a way, and that's the way we like currently following. And so it all comes from a simple idea. So the replica mean field limit that I exposed to you so far is based on the fact that the individual constituent in each replica that interact randomly with one another are the neurons. Okay, but in principle, you could use the replica trick for a replica model for which the elementary constituents are not individual neurons, but have more structure. And in particular, you could do that for pairs of neurons. So here, what I'm showing is a replica model where I take all the possible pairs that I can form in my original network. And now I'm having those pairs being the elementary constituent interacting with one another. So what does that mean? Is that if that blue guy spikes, it's engaged with that green guy as a pair. So it's always going to send a signal to that green guy. But then when he wants to talk to a red guy, he's going to pick that red guy uniformly and independently across pairs that don't involve blue guys, okay? And so basically, it's a different way to split your network. And there's a mean field problem corresponding to this. And now it's a mean field that involves a pair, okay? So you could play the same game as I told you before, and you would end up with basically a self-consistent functional equation that characterize the generating function of the pair. But now, because you have a pair, it's going to be a PD, okay, a two-dimensional PD. And you recover like those non-local boundary terms that are kind of annoying. But it so happened that for the pairs, and only for pair model actually, you can still solve it. There are tricks. I'm not getting into it. I know François Baccelli has given a talk about that recently, and it's on YouTube, so you can go for the details. The point is, you can find a parameterization of G in terms of two functions that satisfy a coupled Volterra equation. And these are amenable to numerics. And so what can you get with that? So the first thing you can get with that is that now you can have input-output function that are not tied to a single neuron, but to a pair of neurons. And so that means like you give me the inputs to the pair. So of course I have to assume that I'm in a limit where having independent Poissonian input is relevant. Well, then I can tell you what's not only what are the output rates of the pair of neurons, I can tell you the correlation, the pairwise correlation between neurons. And so why such a thing may be of interest? Well, it's of interest because a lot of like the plasticity rules that people use are based on a correlation measure between neurons. So that's I believe very interesting to have those input-output function available if you're in the business of designing plasticity rule and exploring what will be the impact over the correlation of the network. So what else? Then, of course, you have more than input-output function. You can also look at what brings you the ability to predict correlation in the network in terms of predicting the dynamics of the network. And so here I'm just showing an example of like a completely arbitrary but chosen, of course, so that it works, architecture, where basically I looked at an architecture of neurons that are engaged into pairwise interaction in a hierarchical fashion. Okay, so that's typically the kind of architecture where I expect the Poisson hypothesis to be valid. And so, and it also exhibits a degree of correlation because I have this strong pairwise structure. And so here what I'm showing is that basically I compare the replica-mean field and the pair replica-mean field model and show that the rates are better predicted by the pair replica-mean field. And that, okay, this improvement in rate prediction is due to capturing essentially accurately the correlation among pairs of neurons, okay? So there are all different realm of like models you can come about based on those pairwise interaction. That's just one kind of model. But you can again like explore that in more detail by going to François' talk online. Now I want to go to the things I'm kind of working on right now with a student who's going to give a talk later on during the talk, and that's looking at whether or not you can extract temporal information from those stationary mean field limits. And so the goal here is to ultimately being able to have like a mean field characterization from which you can infer things such as transition rate, which seems like impossible, but like let's try to do it. And I'm just warning you, we're not going to succeed yet, but I'm just going to show you in which way we think about this. So we're going to do that in the context of a different set of models, which are exponential models. These are perhaps more biophysically relevant models. These are basically the same as the one the counting model I've introduced originally, except that now it's no longer a counting variable. It's going to be a continuously varying variable x. And that variable will reset, just like as the counting variable, but it also will relax toward a base value. And it will do that in an exponential fashion. And also, we're going to allow this variable to take negative value. It can be positive, negative. So it's no longer going to be a proxy for the rate, because now the rate is going to be obtained as an exponential transformation of this internal variable x, okay? And so you can think basically on this x variable as a proxy for membrane voltage. And so now then the quantity of interest that we're going to look at is the moment generating function of x, okay? So now you have a nonlinear model. So things are going to be a little bit more complicated. And if you carry out the analysis, you realize that this moment generating function still satisfy a functional equation. And this functional equation is going to be more difficult to deal with, at least. Why? It's because now, due to the nonlinearity, you're going to have some non-local term that appears. And actually, this equation is going to become a delay equation. Okay. And so this seems a big challenge because delay differential equations are by nature infinite dimensional, and it's very few of them can be solved analytically. However, here in this case, there's a trick, and the trick will be dealt in more detail by my student later on. Here, I'm just giving you the flavor. The trick is that within this model, you can actually rewrite the delay term under that form. And now you see that H, which come into play in the intensity function here, which you can think of as the base rate, the base level of spiking of a neuron, can be interpreted as a perturbation parameter. When H is equal to 0, this becomes just a plain ODE for which you can solve. And so then when you have this non-zero delay term, you can hope to form a perturbative series of the solution and hope that it has the right analytical property that you are after, so that it represents a physical distribution. And the whole technical analysis is to show that it is indeed the case. Anyway, so it is the case. And so now you can look at mixed population of excitatory and inhibitory neuron, and you can look at them in feed-forward model as well as fully recurrent model. And the mystery here is that when you put inhibition, basically the replica-mean field limit works all the time. It's not conditioned only to work in feed-forward structure. It works also in recurrent architecture. And we don't have a good understanding why it's the case, but okay, it seems that that it works. So that's a sanity check. But what we're really after is metastable dynamics. So let's look at a model that exhibit metastability. And this is a model like this. That's the simplest kind of metastable behavior you can think of. That's a bistable behavior. So the architecture is fairly simple, right? You have two groups of neurons, each comprising an excitatory and inhibitory population. And basically, there's going to be a cross inhibition in between the two groups. And if the cross inhibition is weak, there's going to be inherent stochasticity in the model, and basically, you're going to be monostable. But if the cross inhibition becomes strong, then one group being active will essentially silence the other group. And because of the symmetry, only one group at a time can be active. And there's like a stochastic switch between group 1 being dominant or group 2 being dominant. So that's it. So that's the bistable behavior. And so basically the kind of thing you would like is give me an architecture of a model, and are you able to give me some interesting feature about the model, such as transition rate between different states? And so that's a very difficult problem, and it's not a model that will be able to be captured by classical mean field model. It's known already. And so the hope is that by a replica mean field approach, you could capture that. So why would you hope this? It's because the transition from one dominant state to the other is essentially driven by the level of noise that is exhibited by the dominant population while it's up, okay? And so the hope is that if you can characterize the variability of the population when it's dominant, you should be able to estimate the escape rate and then the transition rate. And you can do that in a replica mean field limit because also it's a mean field limit. It has a degree of variability because you have a Poissonian arrival, a Poissonian spike delivery. So there's always a measure, a sense of what is the variability of the population. And that's by contrast to classical mean field where everything gets average. So everything is deterministic. Okay, so can we have any chance to actually complete this program? And so here I'm just showing the first slide of the talk of my student, which basically argue that yes, there's hope you can do that. So here, what that slide shows is that you vary the interaction strength in the previous model, and you're going to compare the exact model to the simulation. The exact simulated model to the value you get from the replica-mean field ansatz. So the value you get from the ansatz are in solid line, and the simulated value are obtained in open circle. And you vary the interaction strength. So you expect to switch from a monostable regime to the bistable regime. And so what happened for the replica-mean field limit? Exactly. Okay. So the original system that, yes? No? Okay. So the original system that you simulate is metastable. So that means it's going to alternate between those up and down states. And so basically you can condition to between up and down and measure conditioning to those up and down state. What is the average rate of fire? So that's what you get there. And you can also do the same thing for the internal variable, and you can compute all the moments of the internal variable. And so then, if you think about the replica-mean field limit, it's an infinite size system. And so actually, it will not be metastable, but it will be multi-stable. So what will happen is that the equation that you get in the replica-mean field limit will admit multiple solutions when the metastable regime arrives. Okay, and so that's what is plotted here. Like suddenly you have like multiple solutions, and those multiple solutions actually closely follow the value that I estimated in the exact simulation. Okay, and so basically this is just to demonstrate that like you can capture basically what's happening in the real system, and also what's happening in like the higher moment of the distribution of the system via the replica-mean field. So then we're not there at like being able to estimate or predict some transition rate, but we're trying to get there. But you can also like estimate some other interesting features. So for instance, here I just show an example of something that I find interesting. And it's just saying like, okay, so you have a system that you can explore, and you can exhibit the dependence on the structure of the system. So here that's synaptic weight due to excitation, due to inhibition. I can change them, and I have a phase space. And in red, I have bistability. In blue, I have the monostable regime. And now I can ask a question such as the following: like, okay, let me look at all those values for which I'm going to be just at the transition between bistable and monostable regime, and see how it scales with k, where k is the number, the finite size number of neuron in each of my cluster. Okay, and then, like, if you ask this question, you would realize that, oh, if I bound my dynamic to remain on the front, separating those two regimes, I have to choose k that scales like an inverse square root, just as like the balance model. And so then you can gain, like, you can ask questions that I think would be extremely hard to answer if you were just conducting a brute force analysis by simulating exact models. Like, you really have like a few knobs, and you can basically estimate scaling behavior that would be very hard to characterize otherwise. Okay, I think I'm going to stop here. I just want to remind you that this is work done in very close collaboration with François Baccelli, which is now he actually has left UT last time I heard, and he's now fully at Henri. The two talks I mentioned are going to follow later this week will be given by Michel Davidoff and Louis Liu, and here are the relevant references and my funding. And I think that's pretty much it. I'll be happy to take your question.
Thank you very much. Is there any questions or comments?
Thank you for this nice talk. I have a question regarding the slide just before that, I think. Yes, exactly.
Wait, this one?
Okay. Metastable dynamics, yes. No, the previous one. Yeah, exactly, that one. So okay. Here, when I'm looking at the connectivity between those two pools or those two groups, what I was expecting was rather, if we consider, for example, okay, in my interpretation, each group is like a column, like a cortical column. So what I was expecting that, okay, cross group connections would have been rather based on excitatory connections rather than inhibitory connections, or both of them at the same time. So what is the motivation, or is there a motivation or a physiological motivation behind this connectivity pattern, or?
Okay, so I think I get the question. So it's about like, is there any motivation, biological motivation for considering such an architecture, right?
Exactly. That's
so yeah. So actually, there's one. Believe it or not, but it's not. I wouldn't say it's related to a physiological model. It's related to a psychology study who studies a perception rivalry. Okay, so these are like imagine you look at a cube, okay, in 3D, and it's projecting in 2D, and you have to decide whether and you color how do you call that, a vertex of the cube, and either you see the cube popping up to you or you see it popping up far away from you. And so basically people have been looking at rivalry between like those percepts, and the people have looked at like a neural network that basically exhibit that architecture, and whose dynamics will display the same kind of feature as you would see in this rivalry task. So for instance, they look at the distribution of switching time, and they show that, it seems to like match what has been measured in psychophysics and things like that. So it's more like a phenomenological model. It's not really physiological model.
Okay, I see. Thanks a lot. And one last thing. Did you consider, or let me ask in this way, is there a difference in the weightings of connections which we see in this slide? I mean, between, for example...
yeah. Like these are... these are not the same weights at all. Like you can change them. So if you look at the phase space, I have mu e and mu I. So like there's a mirror symmetry between the two sets of neurons, right? But this is mu e, that is mu I, and they change, right? I explore the space. Then you can put some variability on it. You can put some heterogeneity. Sorry, like there's it will work just fine.
Okay, thanks a lot.
Okay.
Okay, there is a question on internet. So Bruno Cessac asks, how does your approach compare to the Faugeras-Maclaurin results on mean field recurrent models with correlated synaptic weights?
Oh my God, that is way too precise of a question for me to answer. So maybe like, can Bruno tell me what exactly is the approach based on?
Okay, Bruno, could you give more explanation, or could you log to the Zoom link so that you ask directly your question?
So if there's no answer, I can tell you what is a claim of originality, if any. Okay, so that's really this idea of like keeping the finite size structure in replicas and multiplying the system. So I don't know like what the paper is referencing to. But basically all those ideas. Sorry, yeah.
Yeah. I think the paper is about another concept of. It's not really a mean field in the sense that in the limit, the synaptic weights do not vanish, so that you have still correlation in the limits, but you can prove that there is a limit distribution of this kind of. I think.
Okay. I would have to look. I would have to look. So. I guess I would have.
So, okay.
Here I am. Can you hear me?
Yes.
Bruno is arriving. Perfect.
Sorry, but it's just impossible to ask questions from YouTube, and we are asked not to connect on Zoom, so it's a bit complicated. Anyway, if you can hear me, that's fine. Hello, Thibault. Nice to meet you. Yes. Well, in the beginning of your talk, you have mentioned a couple of work on mean field method. Actually, you have forgotten a couple of them.
Yeah, I'm sure. I'm not. I don't claim.
But it's a bit pity because physicists have done so many things. But anyway, here I am talking about the work of mathematicians, actually Olivier Faugeras and James McLaurin. Maybe Olivier is there and he could talk instead of me. But I mean, they were concerned by the point that you mentioned in the beginning, the fact that in general, the synaptic weight in the approach have no correlation. So you get some propagations of chaos and some nice things which make the nuclear work. But they consider seriously the problem when you have a correlated synaptic weight. Well, you need, of course, that correlation with respect to certain number of conditions in order to get a Gaussian limit. But using large deviations theory, they were able to obtain in the midfield limit a nice equation for correlated populations. And I was asking myself if, because you have also equation a bit complex in terms of which involve also correlation, I was asking myself if there are any link between these two approaches.
Yeah, so you said like it's based on having correlated synaptic weights?
Yes.
So you mean, but the synaptic weights are like changing, so like they're evolving?
No, sorry. It's a quenched disorder. So
I see.
Yes, they are fixed, but correlated.
Okay, so there's averaging going on?
Yeah. Well, actually, there is a propagation of chaos. So I think Olivier will confirm, but I think that there is an almost sure convergence result, which means that well, you are a bit above averaging.
Yes. So there's no averaging here, right? Like here it's like at fixed structure, I get a set of equations that can be solved. So like I would say like if there's a benefit to the kind of approach we propose is that we don't ever need like those results, those equations we get never requires averaging. It's just stationary limit.
I'm sure of that. My question is, do the equations that you obtain compare in some sense? Are there any link? Because I mean, there are not so many people studying correlated problems, so it would be interesting to make the link and at least to mention them. Yeah.
Okay. I'll be more than happy to mention them.
Yeah. Thank you.
All right.
I had a small question. For instance, where you show that the firing rate is better explained by RMF than just MF on the plots, yeah. Do you have any estimate on what is the error that you are making with respect to the true system? What does contribute to the error? Do you have an idea of the discrepancy?
So like obviously here I'm like, I mean, obviously it's not obvious, but like I hope I mentioned it when I was talking. I'm cheating in the sense that I confine myself to feed-forward dynamics, right, or feed-forward structure. So basically, when you are in the case where the Replica-mean field limit is supposed to outperform the classical mean field limit, is that sparse case at the bottom, right? And so whenever you miss something, it's because there's still residual correlation, and that's because well, there's that. Okay, there's residual correlation, but there's also another thing: is that in this Replica-mean field limit, you assume that the input is Poisson, right? So if you receive the input from a previous layer, that would mean that the previous layer is spiking in a Poisson fashion. It's not a Poisson process because, right, it has a non-constant stochastic intensity. So something that you will always carry around is, even if you have perfect independence, is that error from assuming that the input is Poissonian when it's not, even so it's uncorrelated. Does that make sense?
Okay, but could you quantify it in the sense that, I don't know, if mu is very small, it tends to be, I don't know if it's mu or beta, I'm lost right now, but do you see, does it mean that the smallest interaction, the better the estimation, or you see, do you know exactly what is,
I don't have,
how to quantify it?
I don't have it in a satisfying manner, right? I could give you my intuition maybe, but no. I haven't quantified systematically the error.
Okay, because in a sense, it seems like it's like a limited development of the true system, right? Like layer after layer, you can incorporate more higher and higher moments somehow between your neurons. And that, if you control like the rest of the series, you know a bit what you're losing.
Yes, you can come with a hierarchy of equation depending on, like, you can decompose your network into like individual neurons, doublet of neurons, triplet, quadruplet, and then you will have a whole hierarchy of equation. But this is something we'd like to characterize. We haven't done it yet.
Okay. Thank you.
Yeah, there's a whole, we're going step by step.
Okay. Thank you. I think, one last question, and after that we need to move.
So, if I understood correctly, you talk about two models. So there was the first GL models, and then there was another version with this spontaneous relaxation towards some basal level of the membrane potentials, which in biological terms relate to electrical synapses. And then you talk about metastability. So if I understood correctly, metastability, it was in this second model, right?
Yes, and it's at the network level. Yeah. And
so, do you think this electrical synapses effect is necessary to observe this metastable behavior or not?
No. So the metastable behavior, the real crucial point is just to have inhibitory neurons, basically. And if you do in my experience, and if you do a spiking model with an intensity function, you need a nonlinearity because this is just the way. And basically, once you have a nonlinearity, you can come up fairly easily with metastable behavior. I mean, that's what. I mean, when I did the modeling of the exact model, it's fairly easy to have an exact model that would exhibit metastability, as long as you allow inhibitory population.
Okay, thank you.
Does that make sense? And if you have inhibitory population, you need a nonlinear rate function.
Okay, thank you.
Okay.
Thank you very much, Thibault.
All right. Thank you.